I mean, that makes it easy to read though, you can just skim.
That is true.
I'm wondering who's doing the INL project in Joe this year. Joe reached out to us about just like, I think he said something along the lines.
One of the,
There's an
INL project got,
improvement,
yeah.
No, you're doing DB's change there.
There's
three INL projects?
There's
Yeah.
two INL for here.
It's the California.
That's over. And Stephen and Kate. And then they're INL, so yeah, we're the only.
Our deep vision one is like trying to find a sensor down there. They've got like a whole list of things, and like, you can't find one that exists.
Hey, Alex.
Yeah.
Oh my gosh, how was I? Oh my gosh. I just knocked it on it. Well, I did. And they just said,
I would say, formal exam.
That's what I was, but it's gotta be the
They
temperature
said, yeah, it was
and
really
the
funny.
pressure that's down there, so. They would have to-
Yeah, I did.
Yeah. it's-
I didn't show them the whole one was. I got a three.
And then they can't bring the same signs. That's it. They have a-
That wasn't bad.
Yeah, no, that's insane. Your project is directly related to their success as a company.
I was so excited I got it on my second try.
That's insane.
You should use RDT that counts.
You can get more groups on it.
Yeah.
It's free, apparently, right?
It's just, yeah, it's just great.
I would have figured they would have gotten a bigger group on that.
Although McNeil did offer Dr. Robbins, I don't know if you know that, he's offered you up to.
You know, my colleagues have been very kind to me. They're trying to keep me busy during the summer, and that's just fine. Oh, all right. Well,
Yeah.
It would be right.
Looks so nice.
I suppose yeah, because they've got a July 4th target date, right?
Yeah, they need to go.
So it
sounds like
more like a September.
Okay.
Date. No, I wanted to ask.
They're-
I know.
Oh, they have-
But it has to be.
To
get the funding, it has to be delayed.
They're already like digging the hole, so.
They broke ground, did it for last, so. I do that, you know.
Dude,
Digging a hole in some position.
yeah.
All right. So I'm set up. I'm recording. I think I have everybody admitted who wanted to be in. A couple things first. So I got through the grading for the slides 5 and lessons 5 and 6. So Monte Carlo first was the first of those, and I'm relearning the framework. It's called NB grade. You need to see what I'm trying to show you. How to hit that? There we go. When I first put the things together for NE415, that was back circa 2019 or so. And so you've seen the first 4 of those worksheets were the ones from that. There might have been some issues just because they were processed a while back. I don't know if that was part of it, but I've learned some things that you are all doing that I think I can help you avoid to do. So I actually first wanted to show you how these things are set up first, and then like the sorts of issues that I'm seeing. So this first one is, let's see. All right, so this is the source material. This is the notebook that I produce that is then turned into the one that you see and fill out, and that goes back into the system and can be automatically assessed. All right, so I kind of start the way that I do it. I start off and I come up with a problem, and then I solve the problem, and then I turn that solution into the thing that gets deleted, and then you put in your own solution. But I make tests with the thing. So you've seen the output of this, and so if you scored all the points, then you didn't get any feedback. But if you didn't get all the points, then I upload an HTML file that probably looks a little bit like this, but it's rendered in some way. Ideally, I would give you all feedback directly to the submissions, and there's a way to do that. The problem is the only way I can upload a file for all of you for a single assignment is if the file I upload is named the same thing that your assignment is named, which means it has to be a Jupyter notebook, which doesn't make a lot of sense when it's HTML that this is. So I'll have to do some development to get to the point where I'm doing that. But just know that if you do get feedback, if you don't have any points off, I won't give you feedback. Right. If I think that I need to say something, I'll do that just in the speed grader itself. Okay. So anyway, what was the starting point for this Monte Carlo first worksheet? So you had to make this function roll the die, or you didn't have to make it, but you had to fill it out. So you started off with the def and then the x equal random and value equals 0, which just initializes it so that when I return value, it actually returns something. But of course, 0 is not one of the allowable values. You should have 1, 2, 3, 4, 5, or 6. And so when you get it, what does it look like? It should look like this, with a message saying your code there, right? Does that look familiar? Now, the raise not implemented error, I think this was probably discussed somewhere in the notebook itself early on, but this raise not implemented error is there only to make sure that you replace it with your own code. Because if you run this, if you put your code here and you don't remove this, what happens?
Gives an error.
Yeah, it gets an error and you're probably like, what the hell? It's like, oh, just delete it and it's fine. So this is really just a placeholder to ensure that you are actually placing your code. I might be able to get rid of that or something, but in this, I just know that that's there. We're actually going to see raise with some sort of error later today. We're going to be using unit testing. So today's lesson is all about, well, I call it engineering simulation. We're not actually going to be doing the simulation today. You'll continue the simulation on the project, but I'm going to give you some tools that I think will help you put together a good package, a good full solution. All right. So this is what you see in that. A couple other things. If I go to my source material and I click on MB Grader, form, create assignment, I can assign all sorts of things to the cells, right? And so in this case, there are 4 points total. Where do those points come from? Well, if I go here to cell 6, which is set as an auto-graded test, it has 2 points. So 2 points come from this thing. This is a, let's see, auto-graded test, and then so in number 2, roll the die is an auto-graded answer. So in this case, where you see something on your side that says put your answer here, that's a cell that you should be modifying. A cell like this, which has just text, is set to read only. Now, you can change that, I think, on your side, but what happens when I get it is the cell content is replaced with whatever it started with. So I think one of the issues, right? So in one solution for one of the problems, there was an integration that you needed to do. I think for one of the distributions. So you can use, if you've had some Python experience, you might use something like SciPy's quad to do a numerical integration. If you don't know what that is, don't worry about it because that's supposed to be at the end of 415 and we'll get there. But if you import that and try to make a statement like import from scipy.integrate.quad, right? That will import this quad function. You can use that. Quad just evaluates an integral, right, from A to B. So don't worry about it. But if you use that quad function somewhere down here, you might get the right answer when you test it. But this block up here, because it's set to read only, gets totally wiped and replaced with what I started with. The reason for that is you can imagine all sorts of ways that students could adapt the notebook in a way that would, maybe make things better for them. I don't think that's anything that you would want for. I'm not. That is not something that I'm seeing here. It's just if you're not aware of that, that's going to happen, and so that's just something I totally had a blind spot. So if you have something like that where you made an import statement that didn't appear to be there on the feedback that you get, let me know and I'll fix that. But now knowing going forward, the best practice for you is only modify the cells that have a specific request, like put your code here or in the next thing, do this LaTeX. The other thing that I had, and wasn't for this one, it was for the random this is the other one that was great. Yeah. So I had this latex. So I showed you the latex here. My my fault was I didn't show you how to wrap that and actually have it shown up. So here, if you look, this is the latex that I use, and you can see I copied and pasted it there. But to get it to show up in Markdown, Markdown is the type of syntax that we use in the text boxes. You have to wrap it in these double dollar signs. So I saw a couple of folks who hadn't done that, and that's totally fine. It's just I tried to implement something new by having you play with the syntax, and sometimes you miss the small things. Yeah.
I will say that, I forget, but it's supposed to be the inline notation, not just the, equation notation for latex, so that's why some of them.
Yeah. So it's not formal latex, it's latex syntax, but it's like really just a subset of latex. That's it. But yeah, so it's in between dollar signs as opposed to doing equations, they won't recognize. I wonder, does that even work to?
It worked on mine.
So
I did like the / like bracket and. it worked.
Oh, I did the same wrong.
begin
Well, it's
equation.
the inline, think about the,
About latex.
from if you want to do just an equation.
Oh, you're talking about like this? If for
Yeah.
that does not. Yeah.
It did not.
So you can get putting equation doesn't hurt things, but doing the inline does not do that, and I've had that issue before. There might be some markdown instances that do allow that, but that depends on the math backend that it's used. I'm pretty sure it's called Math JSON or Math Ajax that's used here. Anyway, this is just some details on these things to show you kind of like what I start with and what you get. So if you've run into things that just don't make sense to you in the structure, don't hesitate. Let me know, because I like I said, for this material, I'm producing it as fast as I can so that it's there, because otherwise otherwise we wouldn't have the material. So just bear with me. If you see things that are wrong, let me know. I did go and I switched the homework 2 points. Everyone got full points on that. That's the one that had a lot of those buggy things that some of them are probably because you did something that you shouldn't have done. And maybe that's just because it was early on, but some of it might have been me. I think you had one of those issues. And it was something that I could not diagnose. It was something where cell IDs were getting copied, and the NB grader, the framework that does all this, just chokes. And I don't know why. And then some of you had issues where it wouldn't run yourself, but hopefully we're past those sorts of issues. Any questions on this? Are the is that format working reasonably well? I know it's tedious, but it's tedious because programmed assignments are tedious, right? If you to take a set of instructions where you have to go and work through it in the way that you have to do it on these notebooks, that it's hard. But then again, learning is hard. But that is the learning that you're doing. There's no real textbook. I don't have like real reading assignments. That is the studying you're doing. That is your homework, right? You have these projects, but these will be discrete things that are primarily there to give you practice in a less restrictive environment. So the notebooks, you got to do it within that small space, which is why the exercises themselves are pretty small. The amount of code that you should ever need to put into one of these notebooks is pretty small in a relative sense. When we get to the project, you can have more code. That'll be in a Python file, maybe with a notebook, and we'll talk about that by the end of the day. And that you'll have more flexibility. You won't have all the constraints, but for getting the basics down, I think this is a good way to structure your walking through the material. So of course, any feedback you can give me on the way that it's set up, I'm all ears, because I haven't had a chance to get a lot of feedback on these. It was the one time in summer of 2019 that I used these for students online, and then I had a couple test cases over the past year. Some students do some like independent stuff for me to go through them. Not this stuff though, because this is new to this class. So feedback is wonderful. Okay, so on lecture 7, the last time, the one thing that I wanted to go back to was a comment on the errors in estimates, right? I said it, but I didn't emphasize it. When we try to understand the error in, say, the mean that we compute, we'll often need to compute the so-called sample variance. So I put it here almost as an aside, but this is a critical value for us when we try to say, hey, our simulation gave us this answer, but we want to know how good that answer is, and that will need the sample variance, right? Which then leads to what we call the standard error, right? So the sample variance divided by n gives us this epsilon squared. You take the square root of that. That is our standard error. That is the thing that is almost universally used to make statements like this, that we think the true value is equal to this thing plus or minus the error, the standard, right? So that comes directly from the sample standard deviation. And then we played a little bit, and I think we got to this, but then to help you with the homework, I wanted to show you this. So remember the central limit theorem, the point or the value of it is that we can use the population variance and the population mean to say that our observed value x bar should follow a normal distribution with the right mean, and then with a variance that is divided by n. Right, so this is that standard error that we just saw, or the epsilon squared. Okay, so why is it 0.2 and 0.16? Well, if you remember, for one of our cases for the simulation, we could set p equal 0.2. That was like 5 steps that the neutron took. Remember, we started off with a 50% chance, and then it went linearly. So that for the case of 5 steps, we have 4 steps because it was number of steps plus 1. That we divide by. So that's where the p comes from. But if it's a Bernoulli distribution, we also computed the variance, right? So if we have a true coin flip where p is equal to 0.2, the variance of those samples will be p times 1 minus p. So in this case, I don't actually have to use the sample statistics at all. I have the true values of the mean and the variance. Now, when I then run and I get x bar for the case of, let's see, what am I doing here? So I am producing those responses. What did I use for the numbers? So my responses here, I did 1,000 samples with 1,000 neutrons each. So that's 1 million neutrons total, but I broke it up into 1,000 batches. That's what I get. So what I'm showing you here is the distribution of the x bars that I get, the sample mean, right? I expect it to be 20%. That's the true value. I set that. I'm simulating with that. If you look, this distribution definitely is centered about 0.2, but it goes to either side. And I claim that this curve, even though it looks kind of like blocky, is actually pretty darn close to a normal distribution given by these parameters, right? And if you do that and show both the histogram and the normal distribution together, I hope you're at least moderately convinced that the normal distribution captures that dependence. Do you agree? Why does this matter? Because now, if I know how to compute probabilities for this orange curve, which I can, right, using the CDF, and you get some practice that you've got practice problems from last assignment, right? If I know that 95% of the area under this orange curve lives here, then I can say the same thing about the purple curve. And that means that I can say something about the x bar being, it's 0.2 plus or minus 0.02, if this happens to be my 95% bound, right? So that's the beauty of the central limit theorem, okay? The practical issue is many times we don't know what that true variance is, the 0.16. We only know that here because we knew the distribution that we used to generate the samples. So in general, though, we would have to instead use the sample variance, right? So if I had those 1,000 samples, I could compute the variance from that. It might be something like 0.17. Is that going to change the overall story? No, right? If you want to know more details, then wait till later class, like reactor lab, or take a stats class. Just know in general, though, that we can put in the sample variance and this story will be basically unchanged. And I thought that was pretty cool. So on to lesson 8. What we'll talk about today is unit test, the VS Code graphical debugger, and the use of flowcharts, which you should already have seen some basic basic examples of that in some of the previous reading. Okay, so this is a different kind of presentation from the ones that we've been doing. It's very let's say practical tool oriented. Okay, so what you should be able to get by the time you're done with this, and I haven't decided if I'm going to have a worksheet for this one. That's such a different type of material. I'll think about that and maybe just put something that's not a gimme, but something that actually lets you set up and test out unit tests before you have to use it on the project. Okay. But what you'll get out of this lesson is how to use unit tests to build a simple test suite for your code, right? For a specific model that you build. We'll also look at VS Code and how we can do debugging. I'm hoping that you've had some experience doing that. Did you use the debugger with VS Code in like N160 or in CIS 209? 400 you did? Okay, so I'll show you how to work with the debugger. I don't know if I'll have time to show how to use it with notebooks. And I don't know if that's actually like super well supported, but I will show you how to do it directly in VS Code. Then we'll talk about flowcharts, and you'll be able to do it by hand because you'll know what shapes to use. But there's actually a pretty cool markup language called we'll see it in a bit, but we can generate some nice looking flowcharts without too much effort, and it actually is a nice way to work on the logic of putting these things together. And so ultimately, what I'm going to show you is kind of an extension of what I started to show you last time, is how we can use Python modules, like a .py file, along with the notebook. So the way that I view this is the Python file, the module that has, say, run simulation, like last time's example did, that's like the engine, that's the back end of what we're using. We're using the notebook primarily as the front end, sort of a lightweight GUI for our code, right? We could actually make some GUIs, and maybe that lives in this class later on. But for now, we're going to be using the notebook primarily as a way to inspect and play along with some of the things that we are developing in the module. So one other thing, you've noticed that I'm using my Jupyter notebooks as slides. If you were wondering how to do that, you can actually install Rise. I forget what Rise stands for, but that is the tool that I'm using to turn these notebooks into slides. And then if you, so I uploaded this notebook to Canvas, and then if you install Rise, you should be able to click the Rise button, which you can't see it here, but that is this thing up here. So by default, you won't see this icon. You probably just see the keyboard if you happen to be looking at a notebook right now, but then you have the Rise slideshow. Okay. If you want to be able to modify things like what slides are where, you can go to the cell toolbar and slideshow. That's up here. So view, cell toolbar, and slideshow. That's what gives me these drop-down menus that I can say it's a slide or a sub-slide, which is that modifies the way that I go through things. But you can also put things that are skipped, which I would do like if I have a lot of import statements that I don't need you to see, or notes to myself. So just kind of a notes for using that if you want. Okay. So why would we do testing of our code? Well, there are many reasons. One, because I test your code and give you a number for your grade, you might want to test it first so that you know what you're going to get. And in fact, you're doing it. You've been doing testing all along in the worksheets because you have been seeing these assert statements, like making sure certain things are true, right? I didn't explain exactly what an assert statement is. You probably picked it up out of context, but unit tests take that one step further. It will make use of assertion statements. We will get some feedback. One of the best things that I like about unit tests is they will make bugs reproducible. So back when I was a PhD student, I wrote a very large C++ code for doing neutron transport. And I was never a big user of the debugger, and I'm still not a big user of the debugger. There were some rare cases that I would use it, but I found that if I did a test-driven development, meaning that I have some little functionality that I'm adding, like maybe computing the distance a neutron travels, right? I would implement that function and then have a test case immediately for some known inputs with expected outputs. Like if I give a cross-section of this, and a dimension for a cell like this, then I can say the neutron will go this far, right? I know how far it goes across the cell. What we'll do with the notebooks then is primarily view the results of the code. So unit testing can live primarily outside of the notebooks. The notebooks are just going to be our front end, like I said. Okay. The unit test, though, is going to make sure that our modules can keep away from bugs. Where is my canvas? There we go. Okay. So a sort of a simple mental model for the way that we'll organize things. All the Python code that we write, the heavy duty stuff, will live in modules, the Python file that we saw last time. Tests will go into separate test files, and then we can run those tests either from the terminal, right? So you've seen me use the terminal anyway, the Anaconda prompt. We can do it from the notebook, and I'll show that here just because it's self-contained, but generally, we probably want to get good at using the terminal, either the Anaconda prompt or the terminal that you get from within VS Code, right? And I'll show you that too. All right. When we organize a project, so I'm giving you this as the way that I expect your project to be organized, and that project statement should be out pretty soon to you, right? Because we want to sort of do every 4 weeks, and we're in the 4th week, so expect that be live probably by the end of the weekend, and then you'll have roughly a week or so to work on that. I'm flexible on dates, but I want to make sure that we keep moving along. But the way that we'll organize this, and this is a directory structure, so this is what you'll see in a set of folders on your system. We'll have a project, right? So maybe that'll be NE415 project 1, right? Inside of that, we'll have 3 directories, one called notebooks, one called SRC, short for source, and then one for test, which will have our various test things. The notebooks will have a notebook file, and then under source, we're going to have something called NE415 tools. This is an example for today. What this is the module. Okay, now it looks like it's a directory. I've said that Python modules are these Python files, but there's an interesting thing that you can do. You can turn a directory into a module by having a file name init.py with these double underscore, or sometimes called dunder. We'll see that in an example. This notebook is on Canvas, and it actually auto generates all of the code that we're going to do, so you don't have to download a separate set of Python files. Okay, so the other thing that lives in this directory is going to be something called stats.py. This is a module that will have implementations of a couple of the simple functions like sample mean and sample variance. It lives on top of NumPy, but it's used for examples. And then in the test directory, we'll have one Python file that has the unit test. So by the time we're done running this, we have all of these Python files that you can use then to explore how to run unit tests, etc. All right, so to make these files, rather than have you download it, I'm actually going to make them here right from Jupyter. So the things that I'm doing here are I'm importing a few modules. OS is for the operating system. Then there's pathlib, which helps deal with Python file paths, and then something called textrec. Right. So when I run this, it's going to create the slides directory. So I'm in the slides directory. What it's going to do is create the source directory and then the NE415 tools and tests. So you would be doing this not in slides, you'd do this in your project, right? So inside of your project folder would be your source and then your test folder. So I'm going to run that, and it seems like that worked. Okay, quick primer on these things that you're going to see, and maybe I've had a couple examples. The percent sign and double percent sign. These are called magics. This is Jupyter specific. This is not Python in general, but you can use these things in Jupyter to get some special behavior for the environment. So if I have a single percent sign, then I can do something like percent PWD. Those of you who have Linux experience, what's PWD?
Print working directory.
I think it's present working directory, but maybe it is print working directory. I don't know. Anyways, it shows you where you are on the system, right? So if I go over here to, well, maybe give an example. I'll put in a new thing here. If I do PWD, it tells me that I am in my slides directory, right? So I have an NE415 notes thing. That's where I keep all my stuff for this class. And then I'm in the slides directory, okay? So that's one thing. If I wanted to do %ls, you Linuxy folks, what's ls? Yeah, so that would be this, and that's going to list out all these things, right? So I'm slowly chopping away at the lectures. I've got my NE415 things here, and I'll be modifying the 400s, right? So a lot of cool magics that we have. The other type of magic is a double defense sign, and this will affect a whole cell. So these things, one line in a cell, like list out these things. I can affect the whole cell by saying, hey, this whole cell is going to be bash. That's the command line, right? I'm not sure how that will work on Windows because Windows itself doesn't have bash. I don't know if it emulates that or something, but we don't need it. So there's also time, which is something that will help us do, let's say, performance of a given thing. So if we do a function call and we want to see how long it takes, we can use that. The one that we're going to use is write file. So this is just a very quick way to take the contents of a cell and write it to a file. This is a great way for you to like have you have a simple script that you want to run, but you don't want to have to deal with a separate .py file. You can just write it and place it. So that's what we will be doing here. Okay, so what I'm going to do is write file src NE415 tools init.py. This is the line, the magic line, and it's going to write the rest of the cell to a file. What do you see here? It worked, but the cell body is empty. That's actually just fine because the init file does not have to have anything. It's like a placeholder there to make the directory that I put it in look like a module. I'll show you that in a sec. Let me get past here. Okay. So now I'm going to write this. So this is all sort of normal Python code, but the point here is that by having this magic line here, all of this other stuff is going to be written to a text file named stats.py that lives in my NE415 tools folder. Okay, so I'm going to run this. Run. So if you see me typing it, I hit Shift Enter. That's to execute this cell, right? So it's overwriting because I'd actually done this. However, let's take a quick look at the functions implemented. What does this first function implement? It says mean. Is it doing anything unfamiliar? Yeah, so it's sort of a wrapper function for computing the mean of a sequence X. The thing that I'm doing on that first line is NP as array. So even if X is not an array, maybe it's a list of values, it will be treated as a NumPy array. And then we can use the NumPy function. So then it checks if size is equal to 0. Well, we can't compute the mean if it has 0 elements. So if you try to give it like an empty array, it'll choke, right? So this gives you an example of something called defensive programming. What does that mean? You protect yourself against stupid users. If I write a function like mean, and I don't want to have to deal with complaints from users like, why didn't this work? Well, you can protect against possible issues by preventing the user from using it when their inputs are wrong. In this case, there's no need to compute a mean if there are no elements, right? That is sort of a trivial example, but if you use this sort of structure in your code, it's called defensive programming, and you can prevent a lot of headaches by making sure that the inputs to a function are consistent with the assumption, right? A mean should only exist for one or more elements, right? Second function, sample standard deviation. So all I'm doing here is the same thing. And in fact, the takeaway here is that I take the mean of X and then I turn it into a float just to make sure we're dealing with the floating point numbers. And I'm using the NumPy standard deviation function here. The thing that I'll point out is the DDOF equal 1. That is the n-1 that we saw in the definition for the sample variance in the previous slide. So That it's for large enough n, this does not matter. And I mean the number of elements. So just know that this is the standard deviation that we want to use. And with that standard deviation, we can compute a confidence interval. So if this is just a toy confidence interval where I'm saying that we have a mean value, and then we have the standard error. That's the sample standard deviation divided by the square root of n. That's exactly what we saw in the previous slide. This z thing here is a multiplier that we can choose. Now, if I choose it to be 1, that means that my confidence interval is by definition the mean plus or minus 1 standard error. If I put z equal 2, for instance, that would be 2 standard errors. This is important because if we are assuming x is a normal random variable and we choose z to be 1 or 2 or 3, that means that we are giving a confidence interval for x that represents a 68% confidence interval, a 95, or a 99. So anybody start the homework from last time? If you, so yeah, you'll see the very first exercise, you're computing some probabilities for the normal distribution, the standard normal distribution. One of those things that you do, 3 of the values are integrated from -1 to 1, -2 to 2, -3 to 3. That's what we're using here for the confidence intervals, right? It's the probability under that bell curve that captures 68%, 95, or 99. So we won't go into any more depth. I just put this here as like an example. And then the final one, clamp. Just make sure that we have values that are in some bound that we care about, right? So we call that clamping. So I overwrote that. Let's move over here. All right. Let's write some tests with unit test. We have those functions. That's our module. They all looked good to me, right? Did you see any bugs? I probably didn't give you enough time to look. I don't think there were any bugs. But what we'll do is write some unit tests to make sure that there are no bugs. So a test case that we'll see in the next slide is a group of related tests, right? Unit test itself is a module, so we'll import it. And then we'll use test case, which is a class that is provided by unit test. Question, for those who have had 2 and 9, did you use class definitions at all? Did you make a class in the Python language? Yeah. So for those in NE415, did you use classes? In C++, you use classes. All right. So Python has classes. I'm not going to teach you object-oriented programming, but I will use classes as a convenience. And sometimes when we use tools like unit test, the things that it gives us are classes, and we can use those, right? So the coming slides, it might be some unfamiliar looking stuff, but it's primarily by example that we'll use it. So whenever I make a unit test, I'll probably just go to an old unit test that I've made and just copy and paste and replace. So I expect you to be able to do the same sort of thing here. Okay, so we'll use these assertions to make sure that we give some inputs, we get some outputs, they're equal, they're almost equal, right? Because sometimes we need to be in a range. And then every test should be, number one, it should be small as reasonably possible. It should be focused, meaning focus on one bound. Like so if you've got a function that has a certain range or you're looking for a certain possible pathological behavior, choose a test to do just that. Like keep it very, very isolated, a thing that you care about. And tests should be deterministic. That means it should work the same every time. So if we're dealing with things that are like random numbers, make sure that you fix a random number generator C so that every time the test runs, it's the same. It could be that the test will behave differently if you change that C, but make sure that the test itself stays fixed. And if you need to change the C to maybe make a different test, right? So deterministic, meaning always predictable. All right, so we'll make these test cases, again, using this magic to write out the thing. So from the top, we're importing the unit test module. We're going to import NumPy. And then this is kind of the cool thing. We are importing from NE415 tools the stats module, right? So why does that make sense? Remember, I am in my project directory, which is slides for me. I created in that a directory called SRC for source. And in that, I had a directory called NE415 tool. And in that directory, I had 2 files. Init, which makes that directory look like the module, and then stats. the actual Python file that I'm importing here. So this is how we get to the stats functions using the structure that I had put in the previous slide. Okay, so just some test cases that we have. I'm going to test a basic mean evaluation. If I give the outputs, the inputs x equal 1, 2, 3, well, what is my mean value supposed to be? 2, right? So I have the 2. So this is my got value. This is what I expected. And then I'm going to check that they are equal to 12 decimal places. Why wouldn't I just use assert equal, which would also syntactically work? So if I got rid of the almost, I could still put in the mean and the 2, but I wouldn't have the places. Why would I want to use this where almost equals is applied rather than exactly equals?
Because you want to use that.
Yeah, so depending on the numbers involved, you might not get exact equivalence. A good reason for this is I'll let you think about this on your own time, but consider the number 0.1, which is equal to 1 over 10. Easy number, right? How do numbers get represented on the computer? Binary. I challenge you to write this in binary, right? You remember, have you dealt with binary a little bit, right? So the decimal system or base 10 system is pretty easy because we have a digit, like digit 1 times 10 to the 0 dot digit -1 dot 10 to the -1 plus digit -2, 10 to the -2. So it's always a number 0 through 9 times the power of 10. Same thing is true for base 2. It's just a number 0 or 1, a bit times the power of 2. So you can write this in a decimal form. Decimal is kind of a misnomer because decimal comes from 10, but you can put it into a fractional form in binary, right? And there's a problem with that. This number cannot be represented in a finite number of bits. So even a number as simple as 0.1 is not represented on your computer exactly. So if you add up 0.1 a whole bunch of times, there's a chance that you won't end up with the correct multiple of it. Right? That's just one example. Usually the floating point system is good enough where you'll rarely see the effect of that. But just know that anytime we are doing things with numbers, we can lose things in the final decimal places. Basically, the numbers that we use, floating double precision floating point numbers, have 64 ones and zeros that define. Okay, what that leads to in practice is roughly 16 decimal points worth of precision. That means that if you are trying to resolve something to the 17th decimal point, you're wasting your time unless you've gone to some other way of representing the numbers. All right, so these are all the test cases. You can take a look at what all the other ones are doing. I'll run this and it's going to put that in the tests / test stats module. Okay, now to run these tests, we can do it from the terminal. We'll also be able to do it in the notebook, but let me actually go here to the terminal. I've got to do this all on the Linux side because I didn't get it set up over on Windows. So conda activate dev cd classes NE415 slides. Let me blow this up a little bit. So notice in my directory, I now have notebooks, SRC, and tests. These are the same 3 folders that you'll have when you run this. Let me go over here to tests. There's my test.py. If I want to run this, I can just follow the instructions here. It says to run it from the project root, which the project root is slides, right? That's but I call it slides because that's where I did all this, but you would do this for a project. If I do Python m unit test -v, let's see what happens. No tests ran. Or if I try to do this with the discover, come on. I feel like my trackpad is dying. Right, discover, let's see if this will do something different. S tests dash P, and then test .py dash V, right? What this will do is look for anything that is a file like test something .py. And then I ran it. Uh-oh, we got our first error. No module name NE415 tools. Why?
Did you mistype what the file was actually?
I don't think so. What I need to do is make sure that I have that module in my Python path, right? So what does that mean? If I'm in Linux and there would be something similar on the Windows side, I have to do something like this: Python path equal Python path, and then I can do, let's see, classes, NE415, notes, slides, and then src. So what this does is it makes sure that everything in this src directory is something that I can import, right? It tells Python where to look for the things that it imports. If you do something like import NumPy, the reason it works is that's part of the system installation of NumPy, right? That when you use conda, that's already there and it knows about it because it's installed correctly and it's put into a certain path. So I'm going to do this and then see if this runs. All right. So all this does is it makes sure that I can find that thing in when I execute it, and it runs, and you can see that everything runs. If I didn't do that, I could go to, well, if I did that, I would have to modify things otherwise. But just know that if you install software for Python, it will automatically be handled in some sort of internal Python path. Okay. I'll make sure to detail this for Windows use as well. I'll adjust it and make sure that I don't leave you hanging on that. Okay. So the way that path stuff is solved right here from within the notebook is this. So where I just did the Python path in the terminal, right in the notebook, you can modify that by adjusting this sys.path. So sys is short for system. It's a module that has a number of things. Sys.path represents all of the file locations where Python will look for modules to import. Right. This goes beyond whatever the default ones are. So you'll automatically have by default things like NumPy and then the standard libraries like math and so forth. But if I wanted to put that system, that's the path for my module in directly in my source code, either in a Python file or here in the notebook, I can do it this way, right? So that it's the same thing that I just did in the terminal, right? So you can use it to, but I will try to get you some information on doing what I just did in the terminal for Windows. And then I can run those same things here in the notebook. You don't have to do it here, but this just shows you sort of all in one fell swoop how the tests are run. So it doesn't seem like we had any bugs based on these tests, right? We want to see all of these tests passing. Some pro tips about unit tests. We want to test behavior, not implementation tokens. If I have a function for solving AX equal B, which is going to be the topic we turn to next week, I don't necessarily care about how I do it as long as I get the right answer, right? I, as an instructor, care about how you do it, and I'll work you through ways to solve that problem. But when we're talking about using unit tests for the code, I am looking for the behavior given some specified input. Right? If I give a certain value of B in a certain matrix A, all I want is the X. I don't care how it was done. It might be the case that some testing would test the performance, like does it solve it in less than 1 second? That's a possible thing to do, but that's not necessarily what I would call a unit test. We want to keep these tests very small. If you notice, all those tests were super, super small chunks of code, right? And pure function. What that means is you'll always have a fixed input and a fixed output. You're not going to rely on some complicated data structure, something we ought to avoid. You do want them to be fast And then if you run into bugs in your code, that is the best time to write a test, right? That's a regression test to make sure that bug doesn't show back up into the code. There are other features of these unit tests that I'm not touching right now. One of them is setup, and then one of them is teardown. This is if you have some pretty complicated stuff in your code where you have to do a lot of work before you even have the data you need to do the test. You see this if you have large software. For your purposes, I think you can use the model that I showed you in the last slide. All right, so that's unit tests in a nutshell. Let me go here and open up VS Code. Oh, great. I feel like it did this to me yesterday too. Like what, why? Oh. All right, so who's used the debugger in VS Code? Raise your hand. All of you? Wait, who has not? All right, so I'll do a quick example of this. So first of all, let me see if I can run this without errors, which means I need my dev environment, right? So then conda activate dev. So if I run this, okay. So this works because I had already set my path in the terminal. If otherwise, I would have to do the same sort of sys import to make sure that I could run this and run the test. So if I have this test here, and I want to stop the execution at that point, right? So I'm going to run these tests, and I want to stop execution when it gets to this definition of X, because maybe it's here where I have an error, and I'm trying to figure out what's happening in my code. So I'll just give you this quick example. This is called a breakpoint. This is where the execution will break, and I'm going to be able to do some inspection of things. So I'm going to run this in debug mode, run start debugging. And I'm going to use the Python debugger. If you haven't run the debugger with a file, you have to do this setup. So now I will run and debug, right? So what has happened? It has gone through all the stuff that is executed for this unit test, and it has stopped there on line 8 in the code that I'm actually executing. At this point, that line has not been executed, right? So we have not set the value of this array to X. So right now, the only thing that I have is this variable called self that shows up as the argument to this function. That's one of the features of classes. Self is the test object, right? So you don't have to worry about that. If I want to take one step forward, I can do this. And now notice over here in the left-hand side, I see X. So I can actually keep track of my variables, right? And if I take another step forward, it's going to actually get out of the function. And then I have gone to the next test. And then I have this with statement and then blah, blah, blah. And I can keep going through line by line, right? So if you look at the lesson 5 stuff for the NE415 materials I gave you, I had the process called tracing. So tracing is where you go through a program and you go line by line, statement by statement, and you keep track of all the variable values in some sort of tabulated fashion. The use of the graphical debugger lets you do this kind of in a way that's not explicitly by hand, but it models that. So I recommend that you be able to execute your code with the debugger so that you can walk through. So it sounds like most of you have already used the debugger. This is just kind of a reminder of how to set it up. The other things that you can do step over, you can do step into. If this were going to be, oh, actually, let me put a breakpoint here to mean. Okay. Right, so I've got my breakpoint there. Then I will do step over. So continue. So if I press this one, it will go all the way to my next breakpoint, which depending on how the order of these tests is done, I might not get. So I'm going to get rid of this breakpoint and I'm going to run this again. And now it'll run. So that's one thing to note when you have all these tests, they are not necessarily executed in the order that you see them here. I think that can be random. So I have my breakpoint here. Now, remember this mean function, that's the thing that I implemented in my stats module. So if I want to step into that function, I can use the step into, and that will take me over to my stats.py. Right? And then I'm here in my mean function and I can keep walking through. So super useful tool to figure out where things go wrong. Of course, there's nothing wrong with the cave person way of doing debugging. What's that? There's that's well, I don't know, would I call it the cave person? Maybe. I suppose the cave person probably doesn't know what code it is, wondering what is this art for my cave?
You read the error message and then you go back through the long list of where it is to the original.
Yeah, so you need to locate the error, have a sense of where it would be. Once you figure that out, what I mean by cave person debugging is you put a print statement. Like the number of times that I have put in code like la 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 la, and then I will have something like print dot 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 dot. Like I want to see the la 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 and the dot 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 dot. And if I don't see the dot 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 dot, I know that something happened between them. That is cave person debugging. Is it good? It can be. It's simple. Keep it simple, stupid. But the graphical debugger is a little bit more powerful. The graphical debugger is also a great way to explore code that you write. So if you want to figure out how something chains together, like how a sequence of function calls gets to whatever answer is produced by this other person's code, you can use this to get a kind of a working knowledge of that. So just a cool tool to use. Let me get rid of these so I don't confuse myself later on. All right. I believe that there is a way to use the debugger from within the notebook. I'm going to skip trying to do that, but you are welcome to try. But the big thing about the notebook is we'll use notebooks as the front end. Import the code that you write in a Python file, right? The exception is in the worksheets, you're going to have little small chunks of code. But when you get down to using Python programming to solve problems, I highly recommend you use modules. If let's say the functions you're writing start to get bigger than like 10 lines of code. If you get 10 lines of code, sure, put it in a Jupyter cell, voila, that's totally fine. That's like true for most like data analysis, like you load in a CSV file and you make a plot, that can be totally done within a single Jupyter notebook. However, if you start doing things like I tend to do, which is get picky about plots and things, you might want to put your plot functions in a Python file and then load that into Jupyter so that you don't have all of the text formatting and things like that kind of clouding up what should be a straightforward looking analysis. All right. So the VS Code debugger, well, I just actually walked you through that. And then we have, you could do, so I didn't use this code. You could use this code if you want. I just worked directly from the file itself, but you could use the debug driver as a way to dive into, say, the mean CI normal function. All right. I want to get moving because we only have 15 minutes, right? Per breakpoints over points. Not button. Use conditional breakpoint, but this is something that I didn't get into, but you can set breakpoints for certain values of a variable. Like so you could have a breakpoint at line 26, but only if the variable by that time hits a certain value. Definitely take a look at some of these things. And if you have questions on how to do more advanced debugging, if you run into something that you don't understand, like what's going on, come and see me. But I think the basics should get you moving forward. Now, the last thing I want to do is illustrate kind of a cool tool. This is the name I couldn't remember before, but it's called Mermaids. So the flow chart that I had in the NE415 notes was written with or produced with some maybe draw.io, I think is what I used. And, that's a cool tool. But Mermaid is a new one that I found because I wanted to find something that was, maybe more codable. Maybe Draw.io was, but in any case, I found this one. So with Mermaid, we can actually use something that looks a lot like code or a lot like a graphical code to produce the chart. So you've got to be able to know how to put the flow chart together in the first place. Otherwise, you wouldn't be making it, right? So you have to have an idea. And this is a really compact text-based way to do it. Like this is their thing. So they actually support a number of different types of charts. This flowchart TD is their, like this tells their engine that you will be making a flow chart. Okay. So in this case, this is an example flow chart. What the different syntaxes are is, so the text box or a rectangle would be a process. That would be what I call in my notes a sequence. That's just a step or a set of steps that are not like looping or anything like that. Just statements that are being executed. Then the curly braces are a decision or what I call selection. That would be like if statements, if else. Then we have the parallelograms, which represent input and output. And then the ovals, which represent a start and an end. So if I take this code and I look over here, so I had opened up Christmas shopping as like one of their defaults, but I put in my own code here. This is the flow chart that I get. So it's actually a pretty nice looking chart. It seems to put arrows and make things around, so it's I don't know, reasonable looking. They have a bunch of other type of shapes. I think the ones I gave are the ones that I have in the notes. So what I will be expecting for the project is that you produce a flow chart that looks like this. You can use this tool if you like, but I want you to follow the basic guidelines that I had in the notes using these things. So it's a good thing to do to help you understand how your own code works, and it's a good way to explain it to others. Anybody ever used this tool before? Yeah, is it similar to draw.io? I saw some head shakes for draw. Is draw.io also sort of like a syntax based? Yeah, all right. That's why which is fine, but I wanted something that was obviously I'd like to program because I can take this and I could put this into a file, a text file, and save it and then store it. That's an image. I can never deconstruct. I could never fix a typo in it. Right. I like text-based things. All right. Some final things. So we don't have to go into a lot of detail, but I just wrapping up some of the things that we talked about and then some other tips. So think of this as a kind of an all-in-one. Here are some tools that should be useful for you going forward. And in fact, a lot of these things are sort of lightweight versions of what I have typically taught in ME701, the development of computer apps for ME, right? The follow-on, I guess, to ME400. Okay, so patterns for using notebooks with modules. Keep the notebook thin, meaning don't put a lot of excess code in it. Keep it like import it, run the thing, write about it. It's like sort of like a scientific notebook, as it were. Okay, so that's where we would define parameters. So if we're running a simulation, that's where you're going to put in the number of neutrons that you want. You're not going to put the full run simulation function, or you're going to just tell the function what to do. Right, and then the module has all of the stuff that we need, and we'll have the unit tests to go along with it. Make imports predictable. What does this mean? You need to be able to set the Python path, or you can use the sys path. And when we have things like in teaching, I always will put. I almost always have Python files that do what I showed you earlier, where I actually just modify the path, because then it's sort of like it doesn't matter who has it; it'll work on the machine. Definitely learn how to set paths for your own models. Now, the one way that you can get around that, and I could have put it in this, and maybe I'll put it in for a later project, is how to install Python modules. So just like you import NumPy or import SciPy or import any of the other things that you've done, you can make a Python module and install it to your system so that in Python, wherever you are on your system, you can say import my fancy module, right? That requires a structure similar to what we've done with a little bit of extra information. I didn't want to cram that into what we're doing now, because it's just probably overload, right? So keep that in mind. We'll probably do that later on. But for now, what we'll do is just set the Python path either in the terminal or as part of sys.path. Just to make sure that you know where these things were living for me, NE415 imports, but it is not a file. So there's no like underlying file, but the stats module that actually does have a file. So you see these double underscores. Anytime you see double underscore, it's something special about Python, right? It's usually not something that you use, but it will often have information that you can use to double check what you're doing. In this case, this just shows me for sure that the stats module that I have imported is in this location. So it's a good way to, sometimes when you're using your own code or importing your own code, you can have more than one version of it. And this is a good way to make sure that the one that you've loaded is actually the one that you want, right? I've had that happen where I've had, some demo module for a class and I set my path. And so I'm actually importing one that's in an old folder, right? I mean, that just means I'm being sloppy, but like in this case, it might be in an old folder when I want it to be the one in this new folder. This is a easy way to make sure that you don't. So when we actually do get to installing, you'll be able to install it. Hit install -e right from that directory that we have, right? It will not take much more for us to do it. -e is important, and for those of you who would plan on so the -e lets you make changes and it shows up. Otherwise, you have to do resetting of the modules, reinstall it, things like that. So think of this as a footnote for the future. Make sure that you know how to do versions. We know how to set seeds for things that are reproducible. We don't want to use bad variable names. We don't want to use globals, right? We want to pass things by functions. And the thing that really matters for your worksheet use is restarting and run all. Because you've noticed the worksheets or notebooks in general can be a little tricky because if you have, say, 10 computational cells and you're down at number 7, you compute it, and then you go back to computational cell number 3 and run that becomes cell number 8. So you can get the execution of them out of order. That's one of the weird things about it, and that can actually lead to tricky things for beginning programmers. Part of how I've set up the notebooks is to avoid that, but I'm not perfect. So if you run into issues or you have suggestions where I might clean up things, let me know. But that is something that's why I have you do the restart and run all, because that forces the linear execution. We can always, so anytime we do unit tests, anytime we create a new function, we should have a unit test, usually 1 to 2 small examples to be started off in a notebook. This is something that I do routinely. I like the notebook because it is so visual. I have results that are there statically, right? Because otherwise, if you run a program, maybe you get a print statement that goes to the terminal, right? But if you want to see all sorts of print statements in a row, the notebook is a great way to do that. Now, the minute that you write one of these new functions, maybe it's that mean function that we saw, test it out in the notebook, and then turn that little test, that little like play that you're doing, turn that into a formal unit test. Right? That's a good way to go from sort of a sandbox to reality. And that was the last of the tips. I got rid of the other ones that I was thinking about doing. That leaves us about 7 minutes. Any questions? Has anybody used unit test before? All right, maybe I will put, I'll put a very short homework together that'll be due on Sunday as well, but it will be mostly, it won't take very long. It'll be just a proof of principle on using unit tests. I expect you'll be able to figure out the flowchart thing, so I'll leave that for the project, and then debugging. That's a really tough one to grade. So I won't do that. So if you don't have any other questions, you are free to go. Have yourselves a great weekend, and we will regroup on Tuesday for a first lesson on linear algebra. Whew. Yeah. That means I have a lot of work to do.
Yeah.